please, going to have a very, very warm welcome for our first keynote of today. It's Thomas Nowotny. There you go. Hey,
Thank
Thomas.
you so much, Adam.
Thank you. Over to you.
Thank you. And gratefully, you already have given half of my introduction for me, so I can just dive right in. When ChatGPT first came out, soon after, there was an article in the register that was called AI Me to the Moon. And they were calculating that training ChatGPT had cost as much energy as driving a car all the way to the moon and back again, like the same distance, which is at 770,000 kilometers, is about like 4 lifetimes of a normal car. And here, cheekily, I had AI generate this image of a car driving to the moon just to lighten it up a little bit. But this is only the beginning. The more shocking trend is that these systems start scaling, and this is for a reason, because people believe that scaling will make them powerful at a crazy rate. So what you see here is from another article. It's getting a bit dated now. It's only going to 2021. But we see in gray the original Moore's law, 2 times faster every 2 years for the computer hardware. And then you see how the different AI systems have scaled over the years. And they have in blue the kind of standard artificial neural networks. So this is kind of convolutional neural networks, image recognition tasks, and things like that. And then in red, the transformers, they are the underlying large language models, including ChatGPT and Gemini and so on. And you see in 2021, GPT-3 just made it on there, but by now we're kind of somewhere here. And you see it's a shocking trend. If you just do this increase every 2 year kind of figure, then the transformers in this log plot, if you make a regression, come out at 750 times every 2 years. And everyone who understands a little bit about exponential growth can see that in about 3 to 5 years, that would be using all the energy we produce on Earth. And we already had the number of half the data center flops are being used for AI. Right, so that's a crazy number. And we see it in the public as well, that they were talking about building new nuclear power stations, that AI is the best thing that ever happened to fusion research because we can't do AI without fusion reactors and so on. So there's a real cracking point coming very soon. Now, that's not the only way to do intelligence, though. If you think about the human brain uses only a power budget about 20 watts, energy-saving light bulb size, to do still quite similar tasks like the AI can do. In some areas, we still may be ahead. So what is it that we could do? Maybe, can we get some more inspiration from the human brain, how we can do AI more efficient? And that's what this talk is going to be about. This is not a new idea. People have been thinking about this for a long time. And while neuromorphic computing started more out of curiosity back in the 80s, now the main selling point is that it could be much more energy efficient than standard GPUs and standard artificial neural networks running on those GPUs. And I just put you here a few example systems that have been built over the years, from kind of the small-sized systems like the Synsense Spec, the Loihi type of systems from Intel, to these big research computers that were built in Manchester and Dresden from academic groups. Now, this has been going on for a long time, and you can see by the scale of this that to get to a kind of supercomputer size, you must have had some development. On the other hand, we don't actually have the neuromorphic products. So if you have a smartwatch, that's not neuromorphic, or your phone, or your home PC. So what is the holdup? I mean, other technologies that started at the same time are now your standard technologies. And I would like to argue that one of the holdups is that we don't really know how to do the software for these. And that's the area I work in. The paradigm that these systems use is the so-called spiking neural networks. And the problem that we have been facing is that people did not know how to actually efficiently train those spiking neural networks to a level that's comparable to what we can do with artificial neural networks. So what is a spiking neural network? Here's the kind of most simple type, but it's also the most prolific type. So 99% of all systems, I would say, are using this kind of paradigm. you have neurons and synapses, like in an artificial neural network and like in a brain. And you describe the neuron as a continuous time dynamical system with a voltage and a current, so this V and I on here. And the simplest is the leaky integrated fire neuron, where the equations are literally like shown here, just an exponential decay of any kind of larger values you have. So as V is larger than 0, then it decays back exponentially towards 0. And then the I is the input current, right? It drives the voltage back up when there's input from other neurons. And the input current also exponentially decays. And the input then between, the interaction between neurons then is this kind of instantaneous interactions of steps or jumps that I show here. You have a spike condition. Whenever the voltage gets over a certain threshold, the neuron emits a spike. And this spike then adds input current according to a weight down here, WJI. So that the next neuron gets that information that the spike has happened, and the voltage of the neuron that emitted the spike is being reset. And that's the most simple one, and there are some names here of other, we won't worry about them today, but there are more complex neurons that have more internal dynamics, that can have longer memories and things like that. Okay, so that's the basic operating principle, and then how do we make that do AI? Well, we built a neural network, and here's one of the kind of most simple, basic tasks that you could imagine, just to illustrate how this works. Yeah, so this is recognizing handwritten digits. There's one of these classical MNIST digits here, a 2, and then you have this as a grayscale image, and you translate it into spike times. So now you have here along the vertical direction, you have neurons. Along the horizontal direction, you have time. And each of these dots would be one of these spike events. So this is an encoding stage where you go from the image, and the grayscale determines where these dots are. And that's the input to a neural network that can, in the easiest case, look like this. You have an input layer, a hidden layer, output layer. All of these hidden and output neurons have these kind of internal dynamics. And then these equations happen here, and these are the weight matrices that I was talking about that transport spikes from here to there and affect the neurons. And then you have a readout where you say, okay, we make these non-spiking and just look at the highest voltage of all these neurons, and that's our readout. So if the second one here, 0, 1, 2, if this one's the highest voltage, then we have recognized the 2, and that would be correct, right? That's the simple scheme. So this is pretty much like artificial neural networks work, except for inside we have these continuous dynamics plus spike events kind of operation. And then to make this network do something, originally we start with random weights, and then it does random things, so it won't recognize any digits. And to make them recognize it, we use gradient descent. Like 99% of all other AI, I mean, we tend to forget this nowadays, where we're looking at the high level, what the large language models can do and so on. But the way they're trained is literally gradient descent, right? So the technology inside is still this, right? So if we want to do spiking neural networks at the same level and want to do the same task, we need to figure out how to do this gradient descent efficiently. So just very intuitively, how does gradient descent work? You have a loss function here called L, and that measures how good your output was. So typically, when the loss is high, the output's very bad, and when the loss is low towards 0, then the output is correct. And then this is a differentiable function with respect to your weight parameters, and you can calculate this derivative, dl dw, and that gives you the direction in which the loss increases, and if you take minus that, it's the direction of weight changes you need to make to decrease your loss. And decreasing the loss means making the network do what you want it to do. And so that's what you do. You make a weight update after a trial and say, the new weight is the old weight minus some learning rate, eta here, times that gradient. And visually, it's simply like this descending a hill of loss, right? So you go down further and further in steps until you find the minimum, and that's where the network's doing its thing perfectly. Right, so I hope everyone's with me. This is very simple stuff, I know, but I never know quite where the audience is in their thinking, so this is the main introduction. Now we can get a bit more technical. What was the problem now with spiking neural networks? Why couldn't we do this like in 1980? And one of the problems is that by the formulation of a continuous system plus jumps, it becomes non-differentiable. The loss becomes a function of the voltage, and the voltage is non-differentiable when the jumps happen, right? So that there's some problem there technically. And people have struggled with that for a while. And one solution, which is arisen in the last 5 years or so, is to use something where you discretize your system and then optimize it more like an artificial neural network. So this is discretized and optimized as the approach. So you take a numerical integration method like an Euler algorithm, turn your ODEs into a function system of discrete updates that way. And then what you actually get is what typically is thought of as a recurrent neural network in artificial neural networks. And then you can use PyTorch and the whole machinery you have available to do a normal so-called backpropagation through time to calculate your gradient of a loss. So you can kind of hijack the artificial neural network world and efficiently learn these systems now. The only problem you still need to overcome is that in this calculation you still have this non-differentiable step function, the Heaviside function, and the trick there is just to replace its derivative, which looks terrible, this pink here, whereas everywhere is 0, and then some infinite value or something at 1. That's terrible. You replace that with something smoother, yeah? So just ad hoc. And it turns out that that works very, very well. So that's where half of the field is at the moment. But there's also an alternative that I find more appealing, which is an approach of optimized and discretized. So you stay with your differential equations for a while, and you try to calculate this gradient of the loss actually in that world of continuity plus jumps. And that can actually work, and this is also something for unknown reasons only being discovered recently. It's something that was known in control theory and physics much longer, but it hasn't been applied to the spiking neural networks before. So this Eventprop algorithm that I'm going to talk about came about only in 2021. And the idea there is that if you have a loss function that looks like this, that is either a function of the spike times, or it's an integral of these voltages and some function of those voltages, then you can actually do the math exact without this trick of smoothing out some kind of step function, because it turns out that the first bit here, the dependence of these spike times on weights is actually differentiable. There is no problem. And here there is a problem, but you can trade it off. You have the integration and you have a differentiation. You can trade off against each other to not get infinity. So this is a bit technical, but it's a well-known method coming out of optimal control. It's called the Adjoint method. And these two PhD students, very bright people from Germany, have developed this now for the leaky integrated fire neurons and the synapses I was talking about. And it results in a system like this. And don't be afraid by the many symbols. It's quite straightforward what you need to know for the purposes of this. So the forward pass I was already talking about. So this is how the neural network behaves when it actually does inference and is trying to produce an output. Yeah, and that's, again, these voltages that decay when they're excited, and the currents as well. And they excite each other by these kind of jumps. This is when the spikes happen, and this is the kind of transitions that happen when the spikes happen. And you can now calculate your gradient by adding a so-called adjoint system that looks like this. It has a backwards dynamics, so it goes backwards in time. So here now the prime here is a derivative backwards in time. And it has exactly the same structure. You see, it's also these kind of exponential decays, and they're being coupled in the same way. And you have some sort of jumps at the times where the spikes happened in the forward pass. That's this kind of condition here. So you can do this, and intuitively what's happened is that these adjoint variables, they're called, lambda v and lambda I. Yeah, so it's the adjoint variable to v and the adjoint variable to I. They keep track of what kind of potential loss the voltage of a given unit, a given neuron, could have caused at any given time. Yeah, and that goes backwards in time from not being able to cause any loss at the end because there's no more effect of them. And then it builds up to earlier values could have caused some loss. So that's calculated per neuron, and these are exact equations that track that. And then whenever a spike happens, then actually a neuron affected the output neurons, therefore caused loss. And then there's an attribution through these jump conditions of the loss caused by that spike, okay? That's the idea. And then you can kind of tot up the total effect a weight had on the loss by looking at the sum of these lambda I values at the spike times, right? So you can imagine how that works, right? The lambdas kind of track the potential loss that might be caused right now. And when the spike happened, it actually was caused. And that's what you then add up into the gradient calculation. So of course, there is a full proof behind that that shows that this is the right math to do that, but this is the intuition, okay? And why is this important? Now, you might think, oh, well, it's just another way of doing things. What's important here is that, as I pointed out, the backwards pass looks exactly like the forwards pass. Yeah, in terms of the structure, there's some ordinary differential equations that are simple to solve numerically, and there's some jumps that are straightforward to calculate and only happen when there was a spike. And we have technology to simulate these kind of systems for the last 20 years because we have done them for the forward pass. We have done brain models with that, right? We know how to do this really efficiently on GPUs, on CPUs, on HPC systems. So we have the technology to do this very efficiently, and I show you in a moment that it scales very good with sizes of problems or properties of your network, so that it's actually much more efficient than this other approach I showed, which is also very popular because it builds onto PyTorch and it builds onto TensorFlow and all the technologies there, but it scales much less well than this. So this is for me, this is a big breakthrough for how we can do efficient training of spiking neural networks and therefore then go into a new era of neuromorphic computing actually having powerful algorithms. Okay, so now with that being said, let me show you some results. One of the benchmarks we like to use is speech recognition. And this is a benchmark data set here called Spiking Heidelberg Digits, where you have these 10,420 recordings of spoken digits. People went into a sound studio and they were speaking 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, and so on, 10,000 times. They did it in English and in German. And so you have a 20-class recognition problem where you want to classify, recognize those spoken digits from the sound. And the sound was then turned into these spiking patterns in the encoding stage I was talking about using a cochlear model. Yeah, so this is a somewhat Bayer-inspired way of doing this. And again, this is the same presentation here. So you have time along the x-axis, and along the vertical axis you have the identity of the neuron. It's roughly something like a frequency band, if you want, per neuron. And then this is a spoken 7, for example. Yeah. Okay. And now we've been able to classify these to high accuracies, and I just put a very summary slide here of a few recent papers, and you will notice they're all from 25, so it's been an exploding area for us, that we can do the state-of-the-art recognition of these inputs with the Eventprop algorithm I introduced. Yeah, so we first showed that with some modification, this Eventprop algorithm allows to just recognize those with standard neural networks. However, we had to kind of put a long kind of delay line at the front of it, so it was not quite optimal. Then we figured out that we can also calculate gradients with respect to other parameters than weights in the network, like time constants and these type of parameters. And with respect to delays, so we could make delayed neural networks where spikes appear and then the synaptic current comes at a delayed time, which is a much more powerful paradigm for these temporal tasks like speech recognition. And in the final stage, we were then able to deploy the trained networks onto a neuromorphic hardware, specifically the Loihi chip that I showed earlier from Intel. And I have some more pictures in a moment. And show really, really good energy and time savings in executing that. So just to now show you these highlights that are relevant to the energy question. Yeah, so here's one example of a scaling law in terms of a numerical benchmark. So we're looking here at GPUs executing these algorithms, and we're looking at GPU memory used and at the training time per epoch. And I'm comparing here two different solutions. One is in dashed lines is something along the lines where you discretize and optimize with PyTorch in this example. And the solid lines are this Eventprop algorithm done with our own software on the GPU, based on CUDA in a more basic way. And you can see here on the x-axis is the number of delay steps in the delay learning task. So this is important because the longer you can make these delays, the longer is the time horizon of how you can correlate things over time. And this is a big thing in AI, of course. What's the sequence length? How much can you reason about? How many tokens or how many time steps in this case? And obviously what you see is that the scaling's terrible for this other approach. And that's the ANN approach, so to speak, right? So we can also take it for the proxy of current systems. The scaling is absolutely terrible if you make these delays longer. To an extent where we discontinue these lines here because they're just fully out of scope of measuring at all. Yeah? Or here they break the GPU because it has only limited memory, right? So that's the real advantage, and that comes from, as I said, from this efficiency of the backward pass and the forward pass. Yeah, to be ODEs plus spiking, and spikes are not that frequent. And then the deployment on Loihi here. So here are a few more pictures of the Loihi system. So they come in small form factors and then larger and larger systems. And the main difference to having a normal GPU and CPU computer is that they work with fixed point arithmetic and an int8 weight resolution on those weights in the neural network. And we were able to show that the trained networks we had, they didn't actually lose any accuracy, even though we were downscaling these precisions. And that's something that's also been observed in artificial neural networks. We can downscale the precision of weights and retain the same accuracy. But in terms of the energy and time to solution, we can save a lot. And this is shown in this table here. There's a lot of numbers in here. It's directly from the publication. But let's focus on the yellow boxes. And you can see there the so-called energy delay product. Yeah? So this is the energy used and the total compute time used multiplied with each other for recognizing one speech example. And you can, so it's in microjoules times seconds. And you can see the difference here between a Jetson or a Nano GPU. So this is already a very compact mobile GPU with very little power consumption. But even so, and even though we allowed it to use batching, which is advantageous for the GPU, you see a factor more than 1,000 savings in energy delay product if you go to the neuromorphic system. So this is a game really worth playing. And I would argue with the Eventprop algorithm, we have now ways of doing algorithms that are as successful as INNs normally, and we can deploy them onto these very energy efficient systems. So in the remaining 2 minutes, just a very quick outlook what's coming next. So what I've shown you here and what's so far published is all about this very typical but still very constrained system of leaky integrated fire neurons plus exponential synapses. But it actually is not as if the method, the auto-adjoint method, wouldn't work for other systems. However, no one wants to go and do all those math. Again, I didn't show you the math, I showed you the results, but you can imagine the original paper had about a 3 to 5 page appendix explaining how this derivation was made. You wouldn't want to do that for every new neural model. But it turns out you don't have to. You can translate your specific model and you can represent it in just a more general way and say, oh, let's just assume you have some neuron variables and there's some sort of function of themselves and some parameters in time, and so on for all the other definitions. Yeah, so that a spike condition is just some sort of differentiable functions of the variables, and the jumps are just some sort of jumps. And you can do the general math and then use something like SymPy to do the specific math for any model that you want to actually do. And that we've done. We get the general adjoint method outputs that looks like this, and it's actually much more understandable than the specific one. Just to point out one thing here, yeah, the adjoint dynamics relates directly to the forward dynamics. The capital F was the forward dynamics, and the adjoint dynamics is just given by this kind of easy, simple equation. And so on, yeah, and there's more things that one can recognize, that the threshold, sorry, going the wrong way, that the threshold gates which adjoint variables actually receive the errors in the backward pass, and so on. So I'm not going to go through all the details here. And then you can implement this in SymPy, as I said, for any specific model that you want to look at. And this is an example how you now, as a user, can define your own neuron. And this is the live neuron again that we already had, but now defined by a user by simply giving the ODEs and giving a reset value, giving a threshold function, and so on. And everything else is done in the background. So the full learning and backward pass is defined within the software itself automatically. And it's like AutoDiff in PyTorch, which is a very powerful thing. That's one of the engines that drives current AI research in the background. It's often forgotten, but without AutoDiff, many of these things would never have happened. Okay, and with that I'll summarize. We have modern algorithms now to do spiking neural networks, which means we can now use neuromorphic hardware for actual problems, not just toy problems. That allows good energy savings on GPUs, but more radically on the hardware. And with this new auto-adjoint method, which is still unpublished, but it's coming, it's already available on GitHub. But with that one, I think we're making a breakthrough where everyone can use this technology and train their neural networks more efficiently. And that's all. Here's some acknowledgements of my collaborators and some funding agencies. Thank you very much.
Wow, thank you. Thank you for that whirlwind tour of how we can reduce AI energy output. So, do you have questions for Thomas? I'm sure someone's got a burning question. I'll kick it off then. Where's this research going? Which technologies were you most likely to use it?
Yes. One shouldn't oversell one's inventions here. The areas where spiking neural networks are particularly good for is anything that has a temporal dimension, simply because in their essence, they are recurrent neural networks that have a memory, so they work better in domains where time plays a role. We have seen speech recognition, that's one typical example. Large language models are also an example, because it's all about sequence learning, where you have a temporal dimension. And you can think of more areas. This happens to be at the moment where most of the AI is happening anyway, but you wouldn't do image recognition with these, right? Image recognition, the image is known from the get-go. There is no temporal dimension to it. It's not building up, and you wouldn't do some kind of streaming processing of an image. At least if you're sane. Some people do it just for the fun of it. So anything that has to do with sequences, that has to do with time, spiking neural networks are a good choice. And we envision them, because of the neuromorphic angle, to just work on the edge. So you could think about replacing your Siri with something that's fully offline. Because, as you know, Siri is going to the cloud and back again to do speech recognition, which seems not only silly, but also in terms of privacy, really terrible. And these systems would be lower power, and you could do these things like speech recognition, in the instrument itself, in the Siri itself, and you could stay local, and it would be much more efficient that way. So that's the kind of thinking, yeah. So anything that happens over time.
Yeah. Questions, Winmo.
Yeah, thanks for the interesting talk. I wondered, in one of the images you showed for speech recognition, where you have the horizontal is the time, and the vertical you said is the neurons, something similar to frequency. Could you expand a bit on the interpretation? I don't fully get the point.
Yeah. So these were produced with a cochlear model, so for an inner ear model. And the human inner ear has this property that it has these hair cells that are on this kind of snail-like structure, where the low frequencies are excited in the front and the high frequencies in the back. So it's a bit like a Fourier transform that the ear is doing of the sound. And that's how these were generated. So they're thinking of neurons as kind of being excited when their kind of typical frequency is high power in the signal, right? And then it makes a spike, right? So when you saw these different neurons, then you could literally think of the the y-axis as being different frequencies, and the dot was where that frequency had a particular high power in a Fourier transform, if you want. Does it make sense?
Yes.
And that's why. Yeah, and then you get kind of these kind of spiking patterns. You can even try to interpret it, right? That like a 7 has a very high frequency component at the beginning, then the A is more kind of like broadband, and then you have another high frequency at the end, potentially for the N. Then you saw that a bit in the spike pattern, but it's not that direct, maybe. Yeah.
Okay, all right, thank you.
Okay, Thomas, we have another question over here.
Yes.
Yes, thank you very much. Exciting. Yeah. So I have the questions about constraints. If you considered optimal control theory, then the optimal solution may come to the limit. So then there are some physical constraints like voltage and current. How do you consider this?
So the connection to optimal control theory that I was talking about is this adjoint method for calculating what's called sensitivities often in control theory, right? Which here is the gradient, basically. So how do I calculate in a hybrid system of differential equations and non-differentiable jumps? How do I calculate these sensitivities to parameters? And that's the adjoint method. I'm not quite sure what you meant with limits. I mean, of course, these things need to be constrained within sensible operating regimes as well. But that's typically done by having, because they're leaky, they're not exploding. But that's not what you meant, maybe.
What I mean is in the original training problem, if you optimize W, there's no constraints. But now you integrate into the control theory, then you have some other variables, like you say, okay, voltage and current, maybe they are limited. So in the calculation, maybe they are outside of the physical constraints or limit.
Okay. Yeah, I mean, so the way this is set up in the adjoint method is that it's a bit like that's why I also mentioned physics, like the Lagrange multipliers in physics, where you could think of the unconstrained system, where voltage and current could have any values at any time, and you optimize that under the constraint that the dynamics actually is a solution of this ODE I was showing. And that's how the adjoint method actually works, right? So it's, in a sense, looking at the unconstrained system optimization under the constraint that the forward dynamics are the forward dynamics of a linearly integrated fire neuron with exponential synapses, if that makes sense. Yeah? So these are the constraints that go with the Lagrange multipliers, which are the adjoint variables. Yeah? Okay.
You said it's a little bit difficult or problematic to use it in images. My question is, since they are neurons and pretty much on a structural way, they, let's say, wire together, fire together, so basically they can be blocks as a CNN, what would be the difficulty here to apply them on structural or spatial feature extractions?
So you can use them on images and do convolution in neural networks, and it will work. But it won't be much more efficient than the artificial neural networks that we already have. That was my comment. So it's not that we can't do it, it's just you don't get that much of an advantage. And that's simply because these work over time. So you would represent your image, like I also did in this example with the handwritten digit. You would represent your image of grayscales as something that is encoded in time. So you need to simulate over a certain number of time steps to represent these grayscales. And that's very wasteful. You're making 255 time steps, but an artificial neural network can do it in one, right? Because you have this translation into spiking activity over time. It's not that it doesn't work, it's fine, but it's not very efficient. And that's why we're looking for applications where that's actually how things operate. And then it becomes very efficient, right? If the artificial neural networks also need to work that way and become recurrent neural networks and do recurrency over a long time, then we're actually much more efficient. That was the comment I was trying to make.
Okay, I think we have time for one quick question. There's someone over here. Where was that? Over here. Yes, hi, David again. Yeah.
David Corliss, sorry for asking a physics question. You talked about the unconstrained system, but the laws of physics themselves are going to offer additional constraints. You mentioned voltage and current, but we know that through a principle in physics called Ohm's law, voltage divided by current is fixed at the resistance of the system. Instead of using an unconstrained system, should we be looking to the laws of physics to identify additional physical constraints on the system that it must follow?
Yeah, I think this might be a slight misunderstanding, of what we were talking. I mean, this is all about how do you approach the mathematical problem of calculating these sensitivities to parameters, these gradients. And all I was trying to explain, and I think that's what the colleague was aiming at there, is that the way you often do this in physics is that you look at unconstrained systems and then put the actual laws of physics in there as a constraint. And that's how this also works mathematically. And that was the whole discussion, I believe. Yeah. So, all these constraints are in there, right? So we eventually only consider things that work in a kind of physical way. These leaky integrated fire neurons are directly inspired by how neurons actually work. It's the actual physics, and this the normal Ohm's law is in there. Yeah, it's there. Yeah.
Thank you.
Thanks. Thomas, just to finish off, are you optimistic that we can significantly reduce our AI carbon footprint to meet our climate needs?
I tend to be an optimistic person, so I think it probably can be done. However, as long as we can get away with just scaling up and building more power stations, people won't do it because it is a bit of a work piece. And going from normal computers to neuromorphic computers is not an easy thing to do. And therefore, I think there will be many obstacles, but I do think with enough pressure and having the entire climate crisis in the background, I think we might be able to, yes.
Okay. Thank you very much. Thank you very much, Thomas Nowotny. And Thomas will be here for the rest of the day, kicking around. And so you continue this conversation. I'm sure some of you still got some interesting